Hello, everyone. Welcome back to the AAS YouTube channel, and this is part of the good stuff. This is the AAS Journal Author Series, and I am very happy to have Kimihiko Nakajima with us today. Hello, Kimihiko.
Hi, nice to meet you.
Yeah, let's see, Kimihiko, where are you located at?
I'm now located at Tokyo in Japan.
Cool, very
Yeah.
cool. It is Northern Hemisphere. Does it snow in Tokyo at all?
No, we don't have usually. And I think this winter is a bit unusual. Yeah, today I think it's very hot, not hot, but yeah, warm, I think.
Yeah,
Now,
yeah,
yeah, it reaches the 20 degrees Celsius, which is unusual in
yeah.
Tokyo in December. But yeah, I think in summer we have very long summer this year, and yeah, everything sounds weird. Yeah.
Yeah. And it is well, it's my Wednesday, December 6th as we record this. It is Kimihiko's morning in December 7th as we go through this.
Yep.
And yeah, it's still quite pleasant in Phoenix, I will say, where I am located. So we're doing good. And Kimihiko, what do you like to do for research?
Usually I'm interested in the distant universe of exogalactic, shift galaxies, how they, form or how they evolve into, into the subsequent galaxies that we see in today's universe. So,
Mhm.
and mostly, and by using some spectroscopic properties, I'm
Cool.
interested in how, what kind of chemical, abundances in the shift galaxies and
Mhm.
what kind of stellar populations, they present.
Nice.
So this kind of things I'm interested in.
Good. Very cool. Very good. And that is going to bring us to this very awesome. This one is an APJ supplement article. It is the open access era, people. This article is open access. You can go get a copy for free. Go get one. JWST census for the mass metallicity star formation relations at Z equal 4 to 10 with self-consistent flux calibration and proper metallicity calibrators. And Kimihiko, take us away.
Okay, yeah, thank you very much. And thank you again for the nice opportunity to present this recent papers published in APJS. And so this paper is written by myself and yeah, and I also thank to the co-investigators, Ouchi, Isobe, Harikane, Iechi-san, Ono, Umeda, and Obi-san for to complete this good study, I think.
Yes, very good study. Good, very good.
Yeah, thank you. Thank you very much. Okay, so in this work, yeah, we make use of the James Webb Space Telescope, super good sensitivity to study the metallicity or gas phase oxygen abundance in the interstellar medium galaxies at redshift greater than 4, which was almost impossible, to do
Yeah.
before the launch of the James Webb Space Telescope. So this is something we can not
Yes.
do observationally, yeah, and to be compared with theoretical studies.
Yes. Cool.
And so I hope many of the audiences know that James Webb is now online, and this evolutionalize the studies of redshift universe.
Indeed.
Especially I'm interested in the near infrared spectrograph non-spec, which covers up to 5 micron. So this the wavelength range between 2 and 5 micron was not accessible from the ground. So this is something we really need to study in detail the properties of galaxies at high redshift universe.
Cool. Good.
And especially in this paper, we focus on the metallicity in the gas phase. So we need to detect some nebular emission lines, like metal lines and hydrogen lines, like oxygen 3 lines or O2 lines and hydrogen magma lines as well, to determine the how much oxygens are there with respect to the hydrogen element.
Yes.
And there are several methods to determine the oxygen abundance in galaxies. And as you highlighted slightly in the top in the next paper, the O3 4363.
Yes.
This is one of the key emission lines which needed for measuring the metallicity in the most reliable manner by determining the electron temperature of the gas.
Yes.
But it was super challenging for us to detect it even at redshift around 1 or at redshift 1 to 3, before the James Webb.
Yes.
But in the local universe, there are many reports of these detections, and by detecting these emission lines, we can measure the metallicity or oxygen abundance in a reliable way, and over the wide range of stellar masses, and we now have how metal enriched proceeded in galaxies with cosmic stars, not with with stellar mass, the function of stellar mass, I mean.
Right. I'm with you.
Yeah, I'm sorry. Yeah. so this is so-called mass metallicity relation. The metallicity as a function of galactic stellar mass. And in the local universe, there has been a tight relationship between these two quantities, and we can extend this kind of studies of mass metallicity relation towards redshift 2 or 3 galaxies before the James Webb.
Yes.
By using some ground-based observations like Subaru, Keck, and BLT, and etc.
Right.
And we somehow see some evolution of the mass metallicity relation with redshift.
Yeah.
In the sense that metallicity becomes lower at a fixed stellar mass toward higher redshift.
Okay.
Yeah, but at some point, people have also noticed that stellar mass may not be the only indicator that influence the amount of metals in the galaxies, but also the current ongoing star formation activity may also another important parameter that also influence the amount of metals in the ISM. Yeah, this is because galaxies have some galactic scale inflow or outflow activities.
Yes.
Yes, which could also influence the amount of metals in the galaxies. For
Yeah.
example, galactic outflow may blow away some metal-enriched gas out of the system and lowers metallicity in the systems.
Yes.
And also the
Right.
galaxy scale inflow from the CGM or IGM may also dilute the systems and lowers metallicity as well. So in this kind of baryonic physics may also be an important things to be considered for the evolution of the metallicity in galaxies.
Yes. Cool.
So this paper try to understand what kind of relationship between mass metallicity and also star formation rate at redshift greater than 4, which is now possible with to perform with James Webb Space Telescope.
Awesome. Very cool. Very cool.
And if you go to figure 1, I think now we start to move to the explanation of the data. Because last summer the NASA has released the first data release of the early release observations of the James Webb Space Telescope, so ERO we call it. And as soon as we saw the NASPEC spectrum provided by the ERO observations through the press release, we are really surprised to see the really beautiful spectrum of NASPEC at redshift of 8.5, which was almost unbelievable for us. The first data release of the James Webb, greatly released this super beautiful spectrum of the redshift 8.5 galaxy, which was we are really it was really good surprise for us, and amazed as well. And so many researchers in the world try to report the detection of the nebula emission lines from redshift 8 galaxies by using the same ERO dataset to try to publish the result of the metallicity at redshift 8 galaxy universe. There are I think more than 5 or 6 or 7 papers from different teams to try to report the detection of the redshift 8.5 galaxies and metallicity stuff.
Super.
But
let's,
yes.
Let's zoom in on one of these.
Yeah, so this is the same data set, but based on our reanalysis, I will revisit later because I'm also interested in this metallicity stuff by using the fast ERO data.
Yes.
And but the other teams are also very quick in publishing the paper on archive, but I also noticed that there are several discrepancies between the flux measurement between different teams' papers. in the archive, in the preprint, I mean.
Okay.
And I thought, yeah, this maybe because this is new instrument, right?
Yeah.
In summer, and so we need to be really careful about how these data reduced and how they are well calibrated or not. We have to be check very carefully these some details of the reduction procedures.
Yes. Yes. Otherwise, you may
Yes, and
conclusions.
if you go to the next figure 2, I think.
Sure. Figure 2. So there's our
Yes,
summary.
figure 2, is one illustration of the discrepancy between the flux measurement in the previous
lines.
publications.
Okay.
Okay, so the main figure shows the Balmer line ratios, H gamma, H beta ratio, and H delta, H beta ratio
I'm with you.
in the bottom,
Mhm.
bottom left panel, yeah.
Mhm.
And usually these Balmer line ratios it is the intrinsic value of the Balmer line ratios are well determined based on the KSB some recombination physics, but it appears in different wavelengths. So the only dust attenuation or the degree of dust attenuation changes the observed line ratios.
Yes. I'm with you. Yep.
Yeah. Okay. And so basically, so I think in the bottom left panel, there is some lines, some curves are shown, and this shows the expected Balmer line ratios by changing the degree of dust attenuation.
Yes. Okay. Okay.
So if we assume this physics is okay for the high redshift universe as
Okay.
well, so all the measurements should follow this sequence of the lines.
Yes. Uh-huh. Uh-huh.
But if when I plot the previous papers flux measurement on this diagram, as shown with some open and closed symbols,
Yes.
and different color refer to different object in the same yellow object,
Yes.
and different symbols refer to different publications.
Yes. Yes.
Yes, the
Okay.
open and close symbols are from previous works, and I noticed that almost many of these previous measurements are not fall on this theoretical predictions, but fall below or fall away from this
They're
theoretical
scattered around it. Yep.
predicted curves. Scattered around, and
Mhm.
of course this may be because something exotic physics may exist at high redshift universe. I don't
Maybe.
know, but
Maybe.
yeah, maybe. But before supporting this kind of scenarios, first things we have to do from the observational side is to revisit the reduction procedure to
There you
see
go.
if the calibration reductions are all okay,
Yes.
and the flux measurements are reliable for the especially faint emission lines as well.
Right.
And so this is so as soon as we saw, I saw some series of the papers based on the first ERO data.
Okay.
I noticed this may be something very serious for the flux measurement
I agree.
in a
Yes.
reliable way, and because the flux relations are essential for the measurement of metallicity. So I take some time to develop some reduction procedure, based on the past ERO data. Yeah,
Yay.
to check, check
Okay.
these flux, calibrations and things. And
Absolutely.
we have indeed need to improve some reduction procedure for the background residual subtractions, or how the 1D spectra are extracted, and
Yes.
how the spectra stacked or combined to produce final
Yeah.
2D spectra products. I mean,
Cool. Yep.
so these things need to be improved, from the default JWST pipeline in the early stage of the
Reduction.
reduction. So by implementing these kind of some details, the results have some improvement, as shown with the field circles. And so the field circle in this figure 2 shows based on our improved spectra, the reanalyzed spectra, I mean.
Yes. Yes.
And now I hope you see that our measurement fall on the sequence as theoretically predicted. Of course, there are still some large uncertainties, but still, I think some improvements have been obtained, I think, based on our analysis. So this is the reduction procedure. 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 So this So
Good.
now we don't need any exotic physics, all of the, measurements
Yeah,
are
it's just
are consistent with, theoretically predicted. So I think, this nicely
Okay.
demonstrates that some flux measurement, especially like H delta, is usually very weak emission line. So to accurately measure the
That is
obtain the accurate flux line ratios. So I think this kind of some improvement of the deduction procedure was needed, I think.
nice. Very cool.
Okay, so now we have developed this kind of some analysis tool for the general mass spec products.
Good.
Okay, and at that point, not only ERO but some ERS, early release science observations, already delivered. Yeah, this is something that for the community, James Webb guaranteed some time, and for the early release science teams to perform their observations, but the data are publicly available soon after the observations. So almost everyone in the world can access to the ERS data.
Okay.
So when I completed the reduction,
ERS.
completed the development of the reduction procedure, there are several ERS data arrived, like GLASS or CS data arrived. So I have compiled all of the this
Awesome.
ERS and also ERO data
Nice.
and reprocessed them based on our developed mass spec, a pipeline.
Yep.
And we have assembled nearly 1,000 spectra from the GLASS, CS, and ERO observations, and reprocessed everything and checked everything. And now we have assembled nearly 200 galaxies at redshift greater than 4
Beautiful.
with the detection of the nebula emission lines. So
Mhm.
this is our sample. So as shown, it's the redshift distribution of the sample is shown in this figure 3.
Okay.
With the red shaded histogram shows our sample progression 4 to nearly 10 galaxies, 9 galaxies contained in the samples based on the ERO and ERS data.
Yes, very cool. Okay.
And also there are several ARMA or other DDT JWST observations in the
Sure.
literature,
Very nice.
nearly 10 galaxies. So we compiled them as well in the sample and to discuss how the mass metallicity relations look like as they shift greater than 4.
Yes, please. Okay. So there's our Z's.
Okay.
And emission line ratios. Let's take a look at oxygen ratios. There we go.
Oh yeah. So this figure 4 shows some line ratios diagrams, and this shows O3, O2 line ratios, oxygen line ratios, but at different ionization stages. So showing some how gas is ionized.
Yep.
And R23, the x-axis shows R23. This is O3 plus O2 divided by H beta.
Okay.
So roughly probing the
plus
gas phase
3 over beta.
metallicity. So
Yeah.
O over H. Yeah.
Yeah. Oh, sure. Yes. It's another way of parameterizing O to H. Huh?
Yeah.
Okay. All
And the
right.
red symbol shows based on our analysis, ERO and ERS data, and they're distributed around there and having a very extreme positions and because the black shades shows the local galaxies distributions based on the SDSS galaxies. So the distributions are quite different from the local galaxies.
Indeed.
And they are positioned at more large R23 and large O3 O2 line ratios.
Correct.
Regions.
Okay.
We show that these galaxies have different metallicity and ionization stages of gas.
Okay. Yeah. Interesting. About 2 orders of magnitude. Wow. Okay.
And I will later use this R23 index to infer the gas phase metallicity for many of the galaxies in our sample.
Okay. Yes.
And if you go to next, next. Here shows this shows another line ratios O3H beta
relative
versus nitrogen 2 divided by H alpha. So this is frequently called BPT diagram.
Okay.
And yeah, this diagram is commonly used to separate star-forming galaxies and AGN dominated systems. And the curves, shown here as some commonly used demarcation curves between galaxies and AGN.
Okay.
And unfortunately, our current sample have not go deep enough to get a strong constraint on the nitrogen 2 lines, because I hope you can see that many of the symbols have just upper limit on the N2H alpha.
Got it. Okay.
So, but yeah, you cannot say anything very conclusively. But at the moment, yeah, we cannot find any obvious AGN in the system.
That's a fair way to say it. Yes.
Yeah. Yes.
Very good. Okay. Cool.
Okay. Yeah, we have checked these things, and I think next figure.
BPT.
Oh, what?
I have to look that one up, I have to admit.
Oh, okay. So, okay, next figure. Okay, because I said that the ERO, fast data release, early release observation galaxies are reported in many studies. So, so I just compare some measurement based on our analyzed spectra with the early report of for the same object, ERO object, to see some comparisons.
Yes.
And yeah, for these galaxies, yeah, we have the detection of the O3 4363. So I said this is the emission line needed for the measuring the electron temperature
Yes.
in the system.
Back out the temperature from that. Yep.
So this diagram shows the comparison of the electron temperatures based on our measurement and the values from the literature. Overall, we are consistent. The values are consistent to each other, but for some galaxies, the temperatures are quite different. The measurements are quite different, especially shown with these red symbols. Yes, this is a very important object because this is the highest redshift galaxy in this ERO sample at redshift 8.5.
Yes. Yes.
And some paper report a super high electron temperature reaching nearly 30K Kelvin, which is very difficult to be explained by the normal stellar populations. So some theorists also try to explain this very high electron temperature in the high galaxies by implementing some additional ionizing sources, for example.
Yes. Got it.
Yeah, but based on our measurement, this object has a electron temperature of roughly 2.2 times 10 to the 4th Kelvin, which is high, but not super high. And so we just but it's just explainable with the normal massive extrapolation. So
yeah,
I think we don't need any exotic physics again.
Calibration. Very good. A direct TE method. Very cool.
Yes.
Figure 6.
Yes. So in our roughly 200 galaxies, there are 10 objects with the detection of this O3 4363 emission line.
Okay.
So the sample is small because as I said, this line is very faint usually, and it's still very challenging to detect even with James Webb's telescope.
Okay.
In the ERO and ERS data.
Yes. There we go.
But these 10 objects are helpful enough to check some metallicity indicators. So please go to the next figure.
Yes. There you
So
go.
as I said, if you have this, this O3 4363 emission, okay, it's okay. You will have a very good measurement of the gas phase metallicity. But for the rest of the nearly 119 galaxies, we don't have this emission line. So for the majority of our sample, we need to rely on some other metallicity indicators to derive their metallicities. So yeah, usually people try to use some combination of the relatively easily observable emission lines like O3H beta, O2H beta, or some so-called strong line ratios.
Yes.
To try to infer the metallicity in an empirical way.
Yes.
So and there are several or many studies reporting how these emission strong line ratios are correlated with the gas phase metallicity. And the different curves show the different papers empirical relationship based on
I'm with
their,
you.
you know,
Uh-huh.
yeah.
Uh-huh.
And there are some, large, uncertainties or, discrepancies between different teams. And so this results in some, large uncertainty on the metallicity based on this empirical relationship.
Yes. Yes.
But we worried about some systematic offset because it could change the view of the, metallicity evolutions at high resolution. So we have to be careful about that, what changes this metallicity, empirical metallicity relationship.
Okay.
And in our 22 paper, so last year, we examined or we revisited this kind of metallicity indicators, how it changes with different galaxies in the low metallicity region.
Yes.
And in these panels, we show two curves, the blue curves and orange curves. So these are from our 22 papers, 22 paper. And so the different color refer to different object with different degree of ionization state.
Okay. Okay.
So the blue symbols shows galaxies with a very high, highly ionized,
Yes.
And orange shows the less ionized galaxies for the same metal content.
Sure.
And you see the systematic differences between the orange and blue curves,
For the different indices.
which clearly suggests that you need to correct for the ionization state in advance.
Nice. Nice.
To apply this kind of metallicity indicators to get the metallicity. Otherwise, you'd get some systematic offset, for example.
That would be the orange curves.
Yeah, especially orange curves. If you assume some orange curves, then you'd get a completely different metallicity value.
Yeah, totally. Not just all unequal.
And we compare this, but these 22 papers based on the local galaxies in the low metallicity regime.
Yes.
So we have no idea if such kind of locally calibrated metallicity indicators are directly applicable to high resolution universe. It is an open question.
Okay.
So in this figure 7, we compare these locally calibrated relationship with the high Z galaxies with a direct temperature measurement or directly a metallicity measured galaxies. As I said, there are 10 objects with the 03, 43, 63 line detection.
Yes.
So they allow us to directly compare their relationship with those previously proposed.
Okay.
And I hope you can see that most of the JWST objects, so with the colored symbols, follow the bluish curve.
Yes.
I propose in the 22 paper.
Yes.
So we suggest that these galaxies follow the sequence with a very highly ionized systems in the local universe. So using this comparison, of course, the sample size is still small, and we need more data to confirm the applicability of the local relationship. But at the moment, we see, okay, there's a nice agreement, with JWST observations and the relationship calibrated or developed in the local universe for the highly ionized system.
Yes. Okay, so that's conclusion one.
So using confirming this nice agreement, okay, we try to use our developed 22 papers metallicity prescriptions.
Yes.
Yeah, for the many of the JWST object without the electron temperature measurement.
Okay. Cool. Very nice. Beautiful plot. Okay.
Okay, so now we have well calibrated. Okay, so this is another empirical metallicity indicators, and this is also something it is useful, and this is a combination of the R23 or the O3 O2 line ratios. This is again again try to measure the metallicity by collecting for the different ionization stages as proposed by Isotop's previous papers. And this is also I think useful.
Mm-hmm.
But at the moment, yeah, the relationship is not well, the
Oh,
observational
that's
data
general,
it's still sparse, and we need more data to confirm the,
always
Cool.
Okay.
Yes.
Okay.
But in this studies, I use our 22 papers result to infer the metallicities
Yes.
for many of the objects.
Yes. There we go.
Okay.
Very good.
Yeah, thank you.
23. Okay. Very cool.
Yes. Okay. And I said there are nearly 200 galaxies in our sample.
Right.
But nearly 40 galaxies do not have enough high signal to noise ratios to obtain a reliable metallicity measurement.
To get that index.
Yeah, using that index. So after applying our empirical method, we confirmed that about for these 40 galaxies we cannot use for the following analysis.
Okay.
So for the metallicity studies, we use roughly 140 galaxies, if I remember correctly. Yeah, for the metallicity discussion.
Cool.
Okay. Okay, figure 4. Okay, this is we can skip this. This is just again comparison with the earlier studies. Yeah, I think figure 10 is the one of the main figure in this article.
This is the money.
Yeah,
Cool.
showing they're showing the mass metallicity relation.
Yes.
Yeah, for the galaxies of ratios greater than 4. Okay, so this shows the metallicity gas or gas phase oxygen abundance, gas phase metallicity as a function of galaxy their mass.
Yes.
And the red symbol shows what we get for JWST object at ratio 4 to 10.
Okay.
And the large star symbols represent some average beam for the 140 galaxies in the sample.
Yes. And then we got Curtis.
Okay. Yes. First, I like to okay. And the other symbols, for example, the dash, there are several dashed and dot dashed lines. So these are the lower redshift results.
Oh, okay.
So these are based on the direct temperature method. So at redshift 0 with the dashed line, dashed curve.
Yes.
And at redshift 2.3 and 3.3 as shown with the dot dashed straight line. In the high mass regime. Yes.
Out by the data.
So these redshift 0 and redshift 2, 3 galaxies are based on the ground-based observations before the James Webb Space Telescope. And now we can extend this kind of analysis to galaxies at redshift greater than 4, as shown with the red symbols.
And the big thick line.
Yes. And now we confirm the presence of the mass metallicity relation.
Yes.
Possible. By using the observational data. There is some increasing trend of metallicity as a function of stellar mass as known in the local and ratio 2-3 galaxies. But we confirm the presence of the mass metallicity relation.
Interesting.
Of the ratio greater than 4.
Yes, interesting. Okay.
And another interesting point is that if you compare our mass metallicity relations to slightly lower redshift galaxies, like redshift 2 or 3 galaxies.
Okay.
Of course, these galaxies cover the slightly massive regime, but if you extrapolate these rosy galaxies relationship, toward lower redshift, toward lower masses, then their position along the similar locations on the diagram, which suggests that there might be no strong evolution of the mass metallicity relation between redshift 3 and redshift 4 to 10. So this is another, I think, interesting suggestion. Based on this.
That curve's not all that different.
Of course, from redshift 0, there's a strong evolution toward lower metallicity for fixed mass, but at redshift greater than 3, there's no strong evolutions over the wide range of the stellar mass.
Cool. That's very, very nice. Nice result.
Okay, and I also like to mention that this emerald green symbols, open symbols, are plotted. This is from the J's data. So JWST is GTO, guaranteed time observation of James Webb Space Telescope, which devote more longer exposure time to detect to probe lower mass or fainter galaxies properties. And this JWST team also published their result on the mass metallicity relations recently. And I also refer to their measurement on the diagram. And in terms of the normalizations and the slope, they are fully consistent with what we get based on the early release observations. So which is something assuring for us to believe that this is a mass metallicity relation, typical average mass metallicity relation.
Yes, very good, cool.
Okay. So the next
result.
figure, I think. Yeah, thank you very much.
Okay.
So the next figure shows some comparison, I think.
That's our MZ. That's our first equation, MZ. We got some average values for the same.
Oh, yeah, so this is some formulations. Yeah.
Good. All good. Okay. Then we got a lot of.
Okay. Yeah. So this figure 11. Yeah.
Okay.
Yeah. So we split the sample into different redshift bins, 4 to 6, 6 to 8, 8 to 10.
Yes.
Because some of you may be interested in the redshift evolution among our sample. But at the moment, we do not see any strong evolution, even splitting the sample into different redshift bins. So among the redshift 4 to 10 sample, no clear evolution is indicated. There may be some metal deficit in the highest redshift regime.
8 to 10.
But yeah, you see that this thick gray long dashed line shows our average mass metallicity relations based on the full sample. Yeah, if you zoom in, there's a thick long dashed gray line. Yeah, this shows the average based on our full sample. So this redshift 8 to 10 galaxies slightly falls below this average relationship based on the full sample, which may indicate some metal deficit in the highest redshift regime, but still consistent with the uncertainties. So it is, we need obviously we need more data to confirm this metal deficit.
Yes, those are growing. Yes. Okay.
Yeah, but at redshift between 4 to 6 and 6 to 8, there's no strong evolution. So these some samples are fully consistent with the full sample. Yeah.
Yes.
And another symbols of or shades shows some cosmological simulation results.
Okay, sure.
To be compared with our observations. So now it is possible to directly compare the results, the observations, and with theoretical predictions.
Yes. We have a number.
So there are several high resolution cosmological simulations. Predictions like fire or illustrious energy, fast light, flares, and astronomers. Yeah. So basically, these theoretical predictions predict more or less similar mass metallicity relations, the presence of mass metallicity relations, but some differences as well. Yeah. In terms of the normalizations and the slope.
Right.
And so these differences comes from the different implementation of the, as I said, some galactic outflow or inflow activities and how it changes with halo masses or star formation activities.
Right. Okay.
So these kind of things are different. Also resolution as well. Some technical, resolution problem also, may cause some degree of differences.
Resolution always matters.
Yeah. But we can do some comparisons and do something. Say something important.
Yeah. No, it's great to see it broken out in these bins. It's good.
Yeah, and especially some illustrious energy, fast light, flares, nicely reproduce our observational data set. In the mass range, we can explore roughly 10 to the 8th or 10 to the 9th solar masses.
Oh yeah.
Yeah, in the lowest mass regime is an open question. Some suggest low metallicity, but some of our galaxies present slightly higher metallicity. So this is something we like to explore further with the coming data set.
If there's a turnover at the lower.
This may be something interesting to for the feedback processes in the low mass systems.
Okay. Nice.
But overall, these some simulations are nicely reproducing our observational data set, which is nice.
They are consistent.
But for the others, like fire simulations, typically under predict metallicities as compared to our observations.
Fair enough.
I see. Yeah, more or less,
Fair enough. Yeah.
Like, 0.5 x or something, on average.
Like yeah, right.
And I think this is because fire usually implement very efficient feedback processes, which eject metal enriched gas very too efficient, I think, and other predict metallicity. And so this kind of very efficient outflow is unlikely, I think. Yeah, for the galaxies.
It's pushing
now we observe.
So it's less efficient. That curve would come up, and it would agree with the data a little better. Yes. Okay.
Yeah.
I'm with you. I'm good. Very cool. Okay, so
this kind of comparisons are now possible. Direct comparison is now possible, which is
which we couldn't really do before. We didn't have that data. Good. Okay. 11.
Okay, so the next part is as I said, if you take into account that kind of galactic scale outflow or inflow activities, as I said, metallicity may be influenced by the presence of this kind of galaxy scale event.
Yes.
So if such kind of outflow, inflow activities present, then the star formation activities are also changed as well.
Yes.
So some people also argue that there may be some additional dependency of star formation rate on the mass metallicity relation.
Okay.
So in the next panel, I'd like to examine how the star formation, if the star formation rate difference is taken into account, how the evolution of the metallicity, the view of the metallicity evolution changes, or not.
There you go.
So figure 12 shows the distribution of the star formation rate in our sample as a function of stellar mass, showing the so-called mass star formation main sequence or something, and so this is distribution. And overall, our galaxies have a very high efficient or high specific star formation rate, very efficient star formation rate for the stellar mass. And by taking into account this kind of efficient star formation rate activities, then in the next figure, I show the 3D relationship between mass metallicity and the star formation rate. Yes, okay. So please go to the left figure first.
Okay, left figure first.
Yes. So this figure shows the mass metallicity relation with some collection factor of the star formation rate in the x-axis. I hope you can see. This is a three quantities relationship. Now take into account the difference of the star formation rate. And interestingly, yes, I need some explanation. Dashed line. I hope you can see the dashed line.
Yes,
dashed lines are based on the redshift 0 relationship.
Okay.
And the black triangles and the squares, yes, are based on the redshift 2 and 3 galaxies.
Okay.
So before the James Webb observations, very interestingly, redshift 0 and redshift 2, 3 galaxies follow the same relationship on this diagram.
Fair bit of scatter.
I'm talking about this, dashed curve and black symbols.
Yes.
Before the James Webb.
Correct.
Redshift 0 and redshift 2, 3 galaxies, have the same relationship on this diagram.
They do.
Which was very interesting and suggesting that some metallicity equilibrium between metallicity and
whatever
star
the
formation and the
yeah.
galactic scale outflow and inflow
Yeah.
activities.
Right. It's reached some equilibrium state. Yes.
Yeah, equilibrium state resulting in this kind of same
it.
relationship on this mass metallicity star
Mhm.
formation rate.
Okay.
And if we overplot our JWST object on the same relationship, on the same diagram, the result are shown with this red distribution.
Yes.
And I think it's a very interesting similarities as well at redshift greater than 4. So from redshift 0 to redshift 4 to 10 galaxies, the same relationship may hold, which is a kind of surprising result for me, and which was not
Very surprising.
expected before analyzing the data. So
Okay.
and to clarify the redshift evolution on this 3D quantity relationship,
Okay.
now I show the light in the right panel.
Yes.
Okay, this now the y-axis takes the deviation from the redshift 0 relation.
Okay.
And the deviation as a function of the redshift.
Yes.
So
Okay.
this dashed line shows no evolution
Yes.
sequence.
Yes, because you're deviating. Yes.
And as I said, redshift 0, redshift 2.3, 3.3, no evolution is indicated
Not really.
based on the direct temperature method.
Then.
And then we plot the red symbols at redshift greater than 4. Okay, as I indicated in the left panel, okay, there's no strong evolution at redshift 4 to 6, 6 to 8 on average. Of course, there's still large scatters present, but on average, no strong evolution is indicated at redshift up to 8.
Yes. Yeah, within half decade.
So this indicates that no redshift evolutions may continues not up to redshift 3, but further up to redshift 8-ish galaxies. Several hundred million years after the Big Bang, which was amazing.
Yes, which is it is amazing.
Yeah.
That
So,
is very nice.
Interesting, suggesting a rapid increase of metallicity and reaching the equilibrium state between star formation, galactic scale outflow, inflows activities.
Interesting. Very interesting.
Yeah. And another interesting, result is a metal deficit in the highest redshift regime at redshift greater than 8.
Yes.
Yeah, you see the this data point falling below the no evolution trend.
Correct.
And prefer some decreased metallicity in the highest redshift regime.
So there might be a
of course
here. Yes.
Of course, I think of course the sample size is very limited, and obviously we need more data to confirm the trend. But I think this is something interesting trend, confirming some rapid increase of the metallicity in this early universe, and quickly reaching the metallicity equilibrium state at redshift around 7 or 8-ish galaxies.
Beautiful. Okay.
So I think this is I think the main results of kind of fundamentality of the mass metallicity star formation rate relation up to redshift 8.
Yes.
But at redshift greater than 8, there may be some deficit of metallicity in the increasing phase of metallicity in the universe.
There's a tantalizing hint of that, yes.
Yeah, tantalizing. Yeah, evidence is exactly.
Okay, very cool. Good. Okay.
Okay, so this is the main result, and the rest of the part is again the comparison with the earlier studies, because, for example, the expression of the mass metallicity star formation rate relation is, I think, is still some people try to understand if there's really something fundamental relationship or not. For example, if we in our main figure 13. For the coefficient of the star formation rate correction factor, I adopt some coefficient 0.66, which is fully empirically determined coefficient that minimizes the scatter on the mass metallicity relation.
That was right here, equation 2. There's your 0.66. Yes.
Exactly. Yes, exactly. Yeah, 0.66 is a kind of magic number that was empirically determined to minimize the scatter on the mass metallicity relation in the local universe.
That's okay.
But for some reason, the same, coefficient works for very high
Across.
redshift universe. Yeah, at redshift greater, up to redshift 8
Uh-huh.
at the moment.
Mm-hmm.
But some other studies also propose different dependence of the star formation rate, and there are several expressions, to try to
Sure.
explain.
Okay.
So the rest part of the figures examine how the result will be changed by adopting different expression of the
Yes.
mass metallicity star formation rate relation.
Yes. Okay. Should we go there?
Yeah.
We'll go there.
Please, look at figure 14. So this is a comparison with, by adopting two different expression of the star formation rate mass metallicity relation. The left panel shows the same, the same as our main result.
Yeah. Right. Uh-huh.
And yes, as I showed in the earlier figure, there's no strong evolution overall.
Right, with a smaller empirical correction. Okay.
Yes. So this is based on the Andrews and Martinez 2013 paper.
Okay.
And we adopt this, the left panel, we adopt this Andrew Martinez 13 paper because it covers the
Bam, 13.
lowest mass regime in the local universe.
Cool.
And developed the relationship down to the 10 to the 7th solar mass,
Right.
which is nicely compared with our JWST observations because it covers 10 to the 7th to 10 to the 9th, solar masses.
Right. A couple orders of magnitude larger. Mm-hmm.
Yeah, so many of the parameter space are overlapped with this Andrew Martinez paper, so nicely compared with their relationship.
Okay.
And the right panel shows another expression from the Mirko Curtis 2020 paper.
Mm-hmm.
And if we adopt this relationship, we see some evolution, some deficit of metallicity with respect to the average relationship, developed by this, authors.
Yeah.
But the main reason we do not adopt the relationship is that many of the parameter space that JWST objects fall are not explored in the original paper, Curtis 2020 paper.
Right, which is no errors.
So we need we need to assume some extrapolation of the relationship toward the lower mass regime.
Mm-hmm.
And to be compared with our JWST objects, and this is not an ideal thing. Of course, we cannot. There's no guarantee we can simply extrapolate the relationship towards towards low mass regime, which is something to be tested. And
Indeed, right. Cool.
So this is a primary reason we adopt the Andrew Martinez 2013 paper for the different local baseline studies to be compared with our JWST objects.
Yes.
But I'd like to mention that if you adopt different expressions and some extrapolations, there may be some offset, appears at redshift around 6, roughly speaking. If you go to figure 16, I think.
Let's go 15 and
16. 16. Please go to
16. I missed it. Here we go. 16. Here we go.
Yes. So this is again the deviation from the redshift 0 relationship. But adopting that, Curtis different expression of the star formation rate mass metallicity relations.
Yes.
So as I indicated in the earlier figures, if we adopt this formulation, larger offset would appear at redshift 5 or 6 galaxies, and many of the JWST objects fall below the relationship. But as I said, we don't think this is. I'm not sure if this is real or not because many of the JWST objects fall on the parameter space that is not explored in the original, relationship at redshift 0. So we need a large assumptions of the extrapolations toward the lower mass regime to get this result. So this is not our main result for that reason. So figure 13 is, and no evolution up to redshift 8 is our main, argument.
Very cool. And just for fun, we're going to visit those one more time before we polish this off. So figure 8 was no, it can't be figure 8. I think it was this one, figure 10. Figure 10 and figure 13.
Yes, figure 10, 13 is a relationship mass metallicity
Yep.
and its star formation rate dependence
Yep.
and its redshift evolution. These are main, findings
Cool.
in this paper.
Very nice. And there are 4 really lovely appendices with some great plots and a summary table of the data in Appendix D. So I encourage you to the full summary of the sample. So go ahead and check that out.
Yes, I hope especially this table D1 is something useful for your
Yes.
studies, because
Yes.
this summarizes all of the detail of the our sample. Roughly 200 objects are included in this table, which summarizes basic properties like mass, star formation rate, some line ratios, or metallicity. So I hope this is useful for your studies.
Oh, I think so. And it goes on for several pages, so you can pull out the data, people. It's very cool. Kimihiko, I want to thank you so much for walking us through your very lovely APJS article.
Thank you very much.
Nice, thank you. And let's see, you mentioned it a couple of times, or you hinted at it a couple of times as we walked through the article. And so I just want to push a little bit on it. And where do you think we go from here over the next couple of years? Is there more observations at the lower mass end? Is there plans to go out to even higher redshifts? Is there additional theoretical work that could be done? So just sort of next steps. Where do we go over the next couple of years?
Okay, yeah, of course. I think, as I said, the low mass regime is something, I'm mostly interested in.
Yes.
And how the metallicity are distributed in the mass regime in the early stage of the galaxy formation, especially, and how it compared with the cosmological simulations. And if it is not, it suggests a very important feedbacks. It may be playing a role in shaping the early stage of galaxy formation. So low mass regime is something we'd like to explore further.
Is that something one can get with JWST?
Excuse me?
Can you go to lower masses there with the JWST?
Yes, I think it's possible. And now I think this article based on the early release observations mostly, and it's relatively shallow observations are conducted, but still we get double data set and and down to 10 to the 7 solar mass, which is amazing. This is simply thanks to the super good sensitivity of the mass spec of James Webb. So by devoting more exposure time for some fainter galaxies, especially discovered by James Webb, because early release of data are mostly based on the Hubble Space Telescope selected galaxies. Now we have large photometric sample based on the James Webb NACAM, which consists of one fainter galaxy. So by targeting these fainter galaxies, James Webb selected objects with mass spec, then we can go for the lower mass regime.
Cool. Okay. Nice. Very good.
And at redshift greater than 8 is another important parameter space, of course. And still it's challenging because by using mass spec, and you can go up to redshift 9.5-ish galaxies. And if you like to use some less frame optical emission lines, but still I think it's useful to see some the tendency of the metal deficit at redshift greater than 8, as we have indicated. So I hope the coming mass spec data set at redshift greater than 8 will confirm or test the scenario of the rapid increase of the metallicity in the high in the roughly 500-700 million years after the Big Bang, and see how the metal enrichment proceeded in the universe. So.
Cool. Very cool. Very nice. Kimihiko, thank you so much for walking us through your very awesome article. And I really look forward to seeing this this evolve over the next couple of years as we probe ever higher Z's and lower M's. Masses will be really good. Very cool. Thank you.
Yep. Thank you very much.
And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.